The next step is to calculate the reaction due to the live load. Here the live load is given as class AA tracked vehicle. So I have drawn a small diagram which shows a class AA tracked vehicle with 700 kilonewton weight and contact length of 3.6. Live load reaction is maximum when the wheel is nearer to the support. So letting the full portion of the wheel within the span, we get equation, or we get the reaction RA by taking movement at point B. That is RA into 15. 15 is the span of the bridge, minus 700 into 15 minus 3.6 by 2 is equal to 0. Consider this 700 as the point load acting on the span. So we get RA is equal to 616 kilonewton. Therefore, the total load is equal to self-weight of the abutment plus dead load from the superstructure plus the reaction due to live load. So if we add all these three, which we have already calculated, self-weight of the abutment, dead load from the superstructure or dead load of the superstructure and reaction due to live load, we get it equal to 942.78 kilonewton. Now this acts as a point load which is shown in figure 1, which is to be considered for to calculate the stability analysis of the abutment. Now we have to also calculate earth pressure by using Rankine's formula. We already know that Ka is equal to 1 minus sin phi upon 1 plus sin phi, and pressure is given by Ka into W into H square by 2. So here we get pressure is equal to 74.25 kilonewton per meter square. Now maximum bending moment occurs at the bottom of the stem. So this abutment behaves like a stem of the retaining wall. So the same concept to calculate the maximum bending moment and pressure is used here. So bending moment of PA will act at h by 3 from the bottom. So h is 5 meters here. So PA we have got as 74.25. So moment due to this pressure is equal to 123.75 kilonewton meter. In many of the textbooks, to calculate this earth pressure, different concepts are used like Coulomb's theory or Rankine's formula. So you can use any of the formulas or theory to calculate earth pressure. Only see to it that you follow the correct procedure. So to do the stability check, again I have followed the same method to what we have followed to calculate stability analysis of retaining wall. So you make a table with component, magnitude, arm length and moment, and use a figure 2 to get the details or to fill the details of this particular table. So first we will consider this figure 2, which is divided into 4 sections. Section 1 being a triangle, section 2 is a rectangle, section 3 again is a rectangle, and section 4 is a triangle. We have to consider arm length from point T. I've marked here it in the figure. So we need to calculate this arm length from figure T. So the first column which says component will give you is equal to the area of the section multiplied by the density of concrete. So area of triangle is half base into height into the density of concrete. Second column gives you the magnitude. Third column is the arm length. So I'll just give you the detail of the arm length for the first component. So if you calculate the arm length from point T, it will be equal to 1.2 plus 0.8 plus 0.6 plus 1/3 of 1.2. So it is equal to 3 meters. So magnitude into arm length will give you movement in kilonewton meter. Same procedure is followed for all the 4 sections. The fifth row gives you the movement due to the point load that is acting on the abutment. This point load is the total load of self weight of abutment, dead load from superstructure and live load reaction, which I have shown in figure 1. And this point load acts at 1.6 meters from point T. So if we add all the moments, we get summation of moments and we get summation of total load, that is W. Now you can go for check of overturning. To calculate the factor of safety, The equation is already given in the first video. So we took summation moment of resist overturning, that is equal to 2025.216, which we got from the table. Overturning moment is the moment due to the pressure which acts at h by 3 from the base, that we have calculated here, which is equal to 123.75. So which is equal to 16.36, which is greater than 2. So the abutment is safe for overturning. Next, sliding. It is equal to mu times resisting forces divided by sliding forces, which is equal to mu times summation W upon PA, that is the pressure. So 0.6 times 1194.3, this is the value from the table, and 74.25 is the pressure that we have calculated here. The value of this is, it comes to 9.65, which is again greater than 2, so it is safe for sliding. The next check is for sinking. Here we need to calculate what is E, that is the eccentricity. To get eccentricity, we need to calculate x bar. X bar is net moment divided by summation W. Net moment is summation M, that is the value from the table, and M is the moment that is generated due to the pressure at h by 3, divided by summation W. Again, this is a value from the table. So here we get x bar equal to 1.59 meters. E is equal to B by 2 minus x bar. B is the base of the abutment, which is equal to 3.8 in total. That is 1.2 plus 0.6 plus 0.8 plus 1.2. Follow the figure. That is the base width of the abutment, which is equal to 3.8. So E is equal to 0.31 meters. Now B by 6 is 3.8 divided by 6, which is equal to 0.63. Now if you compare E and B by 6, E value is less than B by 6. That means the soil below the abutment is under compression. That's the reason it is safe for sinking. If the value of E was higher than B by 6, the soil under would have been in tension and it would have been unsafe for sinking. The last step is to just calculate the maximum and minimum pressure. Again, the equation is given for this. It is summation W by B, 1 plus 6E by B to calculate maximum pressure, and 1 minus 6E by B to calculate the minimum pressure. Thank you.